Imagine a computer so powerful that it could solve certain problems in minutes that might take today's fastest supercomputers thousands of years. That is the promise of quantum computers. But quantum computers are not just faster laptops, they work in a completely different way. Instead of using only the rules of classical physics, they use the strange rules of quantum physics, the physics of atoms, electrons, and tiny particles. In this video, we'll explain what quantum computers are, how they work, and why they could change the future of technology. To understand quantum computers, we first need to understand normal computers. Every phone, laptop, server, and gaming console uses bits. A bit is the smallest unit of information in a classical computer. A bit can be either 0 or 1. Everything your computer does, opening a website, playing a video, running a game, or sending a message, is built from huge numbers of these zeros and ones. Classical computers are extremely powerful, but they solve problems step by step. For many tasks, this works perfectly. But some problems become incredibly difficult when the number of possibilities grows too large. That is where quantum computing becomes interesting. Quantum computers use something called qubits, short for quantum bits. Like a normal bit, a qubit can represent 0 or 1. But unlike a normal bit, a qubit can also exist in a special quantum state where it is connected to both possibilities at the same time. This is called superposition. A simple way to imagine it is a spinning coin. When the coin lands, it is either heads or tails. But while it is spinning, it is not clearly one or the other yet. A qubit is similar. Before we measure it, it can behave like a mix of 0 and 1. This does not mean a quantum computer simply tries every answer at once in a magical way. The reality is more subtle. Quantum computers use superposition together with other quantum effects to guide calculations toward useful answers. Superposition is one of the main reasons quantum computers are so different. With one classical bit, you can store one value, 0 or 1. With one qubit, the system can describe a combination of 0 and 1. With two qubits, it can describe combinations of 0, 0, 0, 1, 1, 0, and 1, 1. As you add more qubits, the number of possible states grows extremely quickly. For example, 10 qubits can describe over 1,000 possible combinations. 20 qubits can describe over 1 million. 300 qubits can describe more combinations than there are atoms in the observable universe. But there is a catch. When we measure the qubits, we only get one result. So the power of quantum computing is not just storing many possibilities. The real skill is designing algorithms that increase the chance of measuring the correct answer. Another important quantum idea is entanglement. Entanglement happens when qubits become linked together in such a way that the state of one qubit is connected to the state of another, even if they are separated. This connection is not like a normal wire or signal. It is a special quantum relationship. When qubits are entangled, the quantum computer can process information in patterns that classical computers cannot easily copy. Entanglement helps quantum computers handle very complex relationships between pieces of information. This is one reason scientists are excited about using quantum computers for chemistry, materials science, optimization problems, and advanced simulations. There is one more key idea: interference. Quantum states behave a little like waves. Waves can add together or cancel each other out. Quantum computers use this wave-like behavior to make wrong answers less likely and correct answers more likely. Think of it like sound waves. If two waves match, they become stronger. If they oppose each other, they can cancel out. Quantum algorithms are designed in a similar way. They try to amplify the paths that lead to the right answer and reduce the paths that lead to wrong answers. This is why quantum programming is so different from normal programming. You are not just writing instructions step by step, you are shaping probabilities. Quantum computers will not replace normal computers for everyday tasks. You probably will not use a quantum computer to write documents, watch videos, or play games. Classical computers are already excellent at those things. Quantum computers are useful for special kinds of problems, especially problems involving huge numbers of possibilities or complex quantum systems. They may help scientists design better medicines, create new materials, improve batteries, optimize logistics, and simulate molecules more accurately. They could also affect cryptography, because some quantum algorithms may break certain encryption methods used today. That is why researchers are also developing quantum-safe encryption. Quantum computers are still very difficult to build. Qubits are extremely sensitive. Heat, vibration, radiation, or tiny disturbances from the environment can destroy their quantum state. This problem is called decoherence. To protect qubits, many quantum computers need special conditions, such as extremely low temperatures, sometimes colder than outer space. Another challenge is errors. Quantum computers need advanced error correction to make reliable calculations. So while the technology is promising, we are still in the early stages. Quantum computers are not magic, and they are not just faster versions of normal computers. They are machines that use the rules of quantum physics, superposition, entanglement, and interference to solve certain problems in a completely new way. Today, quantum computers are still experimental, but they could become one of the most important technologies of the future. They may help us understand nature better, discover new medicines, build better materials, and solve problems that classical computers struggle with. The quantum future is still being built, one qubit at a time.